the record. For this one, before I talk about what is going to be the roadmap for today, I'm just going to remind you of what we did last week. And what we did last week was that we saw so many fundamentals for our reaction for this week. We talked about the functional groups. We saw that the functional groups that we just talked about them on the second week, they are somehow dormant. And sometimes you have to wake them up in order to induce electron mobility and motility in order to form bonds to make new compounds, because making a new structure, new compounds, involves dissociation of the existing bonds and formation of the new bonds. Then as a result, what we're looking for in organic chemistry is that if you see if you see, let's say, for example, a chemical structure, we do not need to just focus on every single corner of that structure. We are going through identification of the functional groups. You want to come to the front? No? Then we are looking for the identification of the functional groups that induces the connectivity and reactivity sometimes with the receptors. That's in pharmacology. Also remember that if you did in biology, we call that pharmacophore. Now, what we are going to do today, we are just going to continue from that concept and do one chemical reactivity. This is going to be the first one thing that we are just going to do that. And as I said, for you want to come to the front? Come to the front. Come to the side. Come to the front. Come to the front. You just argued that you want to come to the front. I took you to the first. I want to go to the front. Yeah, there is jokes. There is no upset. Not so. Now please mute me. You sit here and you sit over there. Huh? You see, everything, you can find a solution for everything. There is no need to sit there and say, I want to go come to the front. Am I right? Huh? Now, the thing that you see the structures on the shared screen. Let's see who else wants to come to. Oh my God, look at her. She also wants to come to the front. You're fine? No, you. Now, then the thing that you just want to do today is this, that I'm just going to start with this structure. As I said, we do not focus at this stage for how to name and call the organic compounds. But the only thing that we care is that we look at the compounds without even knowing the names. We do not get involved with the names to see where do we have to start, how to incite the reactivity of that molecule. And that's all that we care about for this half of the course. Now, when you look at these structures, this is a 3-dimension structure that everyone sees the screen. You see the molecule rotates around. You see that? Or this is frozen for you. You can see that, huh? Yeah, you see that these structures that I have, it is called essentially 2-bromo-butane. We do not care about that at this stage. The only thing which I'm looking into that is that I'm looking for the site of like the volcanic reactivity. You know what is a volcano, huh? That it erupts with lava and ashes. And the functional groups for us, they play the role of a volcanic site that it's just going to burst into lava and ashes. When I look at this molecule, which I know beforehand, this is called the 2-bromo-butane. It has some kind of characteristic chemical and physical activity. We do not care about that. But the thing which I can see over there is this. I see 3 classes of the atoms. The first one, I see that I have a medium-sized balls. The medium-sized balls, you can see 4 of them. We call them, they represent here, they symbolizes here the carbon atom. Then we see, we can see the carbon atom, then we are in the right foot, because now we are working with the organic chemistry. Anywhere we see the trace of the carbon atoms, we see that you are working with the organic chemistry. Now, I see also I see very smaller balls. You see, we have three different ones. The medium size in gray color, it was a carbon. The smaller one in white color, the very small one, they represents hydrogen. And also you see one very singular ball, which is a bigger size compared to the carbon because it has more extensive orbitals. The three dimensions is bigger. And this is in red color, which it reminds you probably like the lava of the volcanic side. This is one of the elements from the group 7 of the periodic table, halogens, which is here. It is going to be bromide. And now we just have it here. That's why we call that 2-bromo butane. Now, these structures that we see, and also you can see that between these elements, there are some sticks around it. For example, there are some sticks between the carbon and hydrogen. And there is no need to remind you, these sticks, it symbolizes two electrons that they are overlapping their orbitals to form a covalent bond. Then you see that these sticks, they represent a strong covalent bond, which connects one atom to the other one. This is in this model that we have. Now, we are just going to go to see, first of all, where is going to be the interesting sites that we have to look into that. For example, you're an archaeologist. Everyone knows what is an archaeologist, huh? If you're an archaeologist, when you just walk along, let's say, in the pyramids, you do not search for everything. As an archaeologist, when you just go to the Egypt, to the pyramids, you are just looking for the treasures. Then if you are an organic chemist, you are not looking at everywhere on this molecule. You're looking for the site of the interest, which is going to be somewhere that it causes the reaction to take place. But before we just start, I'm going to remind you of something. And the thing which I'm going to remind you is this, that remember, in order to induce reactivity, we have to search for a lone pair of the electron, which is not confined like part of the resonance hybrid structures. Then as a result, we can take it to move it around without being concerned that this is not mobilized. And that's the key things that we're going to take from this one. In this structure, from the things that we learned before, we see something happening there. Before I just go to the whiteboard to show the reactivity, I'm just going to finish this one with this very important observation. When I look at this structure, I see every single corner of this molecule is so boring. It doesn't contain any treasure if you are going for treasure hunting at the pyramid in Egypt. Everywhere is so boring because I have hydrogen covalently bounded to the carbon, and there is not much happening there. Hydrogen had only one electron. Now this is shared with the carbon. Everything comes to the octet structure. This is stabilized. The energy just pushing down. The molecule becomes stabilized there. And more importantly, in terms of the electronegativity that these two elements have, hydrogen and carbon, they do not give that kind of interesting thing. In terms of the polarizability, if you subtract the electronegativity of hydrogen and carbon from each other, you see that the electron clouds is not pushed more towards one of the other ones. It's just standing. But look at you two, for example. Look at you two. For example, you are going to go for a pillow fight. Both of you have the same strength. The pillow is standing in between you. You cannot push it towards yourself. You cannot push it towards yourself. You're pushing back. You're pushing back. But, for example, Dalma, for example, joins the fight, grabs one side of the pillow. You see, you're pushed towards him because he has more muscle. He's much more stronger. Then you see, he's not the person to just come and fight with him. He's much stronger. He's a man of higher electronegativity because he has more electronegativity. Then as a result, what we look into this structure, we see that we have these two scenarios. These two elements with comparable electronegativities, they do not induce polarizability to the molecules. But the diamond is the molecule with the red color. Higher electronegative, much stronger. It pulls the pillow The pillow in this case is going to be the electron cloud, shared between these two elements. Then it pushes towards himself, then it gets more pillow. Huh? Then when it gets more pillow, it becomes more negatively charged. Then we see, that's something very interesting happens there. And this polarizability, which comes from a contrast, a huge contrast in electronegativity between bromide and carbon, it's going to be the site that it becomes very interesting. Otherwise, everywhere else you look into that, you find something so boring. Now, I'm just going to stop the share for this part. Then I just go to the whiteboard. But remember, at this stage, we identified the bromide is a site that it bears the treasure there. That's the only interesting site we are just going to go to. Now, I'm just going to stop the share and I'm just going to go right to the whiteboard, which I have it here. Okay. Everyone sees the screen shared? Yes. Yes? Now, look into this one. In this structure that you have, this is the same thing that you had over there. I downloaded the picture. I just posted there. I'm just going to react it. Now, I'm just going to put these structures to bromo, butane. I'm just going to put that inside a beaker of water. Like, for example, you see you add sugar inside the water, you drink it. Instead of the sugar, I'm just going to add 2 bromo butane inside the water, and we see what you may expect to happen. What you may expect to happen. Now, everyone, close your eyes. Everyone, close your eyes. Visualize that molecule inside the water. And visualize you're just going to take a drink of it. After that, just to see if this is going to be safe or not. Now we are just going to see what is going to happen when this comes with the water. Adita, it's okay. Don't fall asleep, Adita. You felt so comfortable. No, I'm kidding. Now, the thing which I'm going to do, I'm just going to put that inside the water molecules. Now, everyone remembers, in terms of the water molecule, everyone remembers the tetrahedral structures of the water, H2O. We have, let's say, for example, the oxygen, and we have what? Let me just put it there. We have the oxygen, and we have the hydrogen with the tetrahedral structures. And you remember from the previous course that you know that oxygen has 2 lone pairs of the electrons. Now, this structures itself is highly polarized because of the contrast of electronegativity between oxygen and hydrogen. At the same time, look into this one. And also I have water. Water acts like the solvent itself. It is everywhere with 2 lone pairs of the electron. The other thing that we see here in this structure, you see that a dummy is going to take the pill away from you, for example. Look at that. What's going to happen? You remember I said that in these structures, these sticks that exist between these 2 atoms represent a shared electron pair. Means that there is 1 electron here, 1 electron there. They are just overlapping the orbitals. This huge contrast of electronegativity, it causes this kind of what? Polarizability. You see that over there. You get extensive negatively charged because the electron clouds, which is shared, is extended towards the bromide because it is stronger with the high electronegativity. Then as a result, the carbon which is left over there, deficient with electron clouds, becomes positively but partially charged, positive delta. That's what we remember from chemistry 1. At this stage, look at this one, what is going to happen. At this stage, we are just going to see that the presence of the solvent, which is polar protics, which is able to form the hydrogen bond, it induces the departure, it helps the departure of, let's say, chloride away, especially the one which is over there. Because this one is going to be dipole, but this one over there. What happens now? We see that because of this contrast of the electronegativity and the presence of the water, which is a solvent, due to the hydrogen bound, induces the departure of the bromide. We are just going to see that the bromide is going to leave this structure. That's what we call that. If you remember from that, we said that the leaving group. We call that they are not the faithful, I should say, friends. I remember when I was learning chemistry, I remember that the elements of the 7 periodic groups, they are not like the faithful wife. They leave the husband right away. Every chloride, bromide, fluoride, iodide, and we have the bromide here. The same thing happens. It acts as a leaving group. When it leaves, it's going to take everything with herself. Guys, I'm not talking about you that become unfaithful. I'm talking about this one. Don't worry. Don't argue about that. No worries. Now, what I'm going to do here, look at that one. The bromide, we call that leaving group. I used to call that myself unfaithful wives. This is the husband, the carbon here. Bromide is the wife. She's very unfaithful. She's going to leave. She's going to get divorced. Now, what happens? When she's going to leave, she's not going to say goodbye. Goodbye, my husband. I had so much good time with you. Goodbye. No, she's taking all the belongings with herself. Every kind of furniture which she bought, anything. But we don't have a furniture over there. This is the lone pair of the electron that she's going to take with herself. The lone pair is what? This bound that we have there, which is shared between them. Then says, goodbye, husband. I'm taking this with myself. Look at this arrow. It takes it with itself. Bless you. Then what you have there? What you have the bromide, which comes outside. This is the wife, took all the belongings with herself, and now she has now 8 electrons. Remember, bromide comes from which periodic table group? 7. How many electrons we find around it now? 8. 4 pairs. 7 minus 8 minus 1, which means that yes, as what we expect, bromide is negatively charged. Now, what happens now there? What will happen here is this. What may happen is here is this one. Now, and now, look at this one. What happens? The thing which happens here is this, that now we have the water solvating the 2-bromobutane. Now, we have 2-bromobutane there. Now, the wife, it was very unfaithful. She was very unfaithful, left. Who is left behind? Carbon, the husband, is left behind crying. Now, look at this one. We dissociated the bond. What's the time right now? Is that as long as we dissociated the bond, let me just restructure it once more because I need to rewrite it. Now, look at this one. This is a carbon. This is another carbon. I just denoted this one here. There is another carbon. I denoted this one here. There is another carbon, and there is another carbon. This one, look at that, comes with 3 hydrogen. I put CH3. It comes, look at that. There is 1 hydrogen behind us in the screen. We have CH2. This one, look at that. This one also is CH3. And also, there is 1 also hydrogen for this, which I'm just going to write it CH. And now we'll just go to a very important part. The important part was this one. I said that whenever in organic chemistry, that was a key rule. You dissociated a bond or you form a bond, you have to stop. And as Aditya said before, you have to find the formal charge of it. What is a formal charge? The carbon which is crying right now because the wife left him, is this carbon here. Then now, this is the one which is breathing. What I'm gonna do, I'm just gonna stand on top of this carbon here, draw my fishing net around, if you remember, to find the formal charge. The first question, if you remember from last week what we did, the first question which I'm asking myself is that I'm standing on top of the carbon. Where is the address? By the address, I mean in the periodic table. Which groups I can find carbon? 4. I can find it in group 4. Now, the second question which I ask myself is that in the fishing net which I throw around the carbon which I'm standing, how many fish? By fish, I mean electron. Don't take your the nose. There is no fishing smell. How many carbons do I have here in the net? Look at that. I have one here. I have one here, and I have one here. How many? 3. Then I have 4 minus 3 gives me +1. That means, I found it. The carbon, which is the husband, which is left alone outside, becomes what? Becomes positively charged. Becomes positively charged. That's what we call that carbocation last week. It becomes carbocation. Now, the thing is that, now when I look at this carbocation, when the husband is crying, she needs some support. Sorry, by husband, I have to use he. He needs some support by the friends. How many friends he has around himself? By friends, I mean the carbons. The carbon has to have a carbon as a friend. How many carbons is around him? 1, that's right. 2 immediate one, which it gives us to a terminology which is very important, which it means that this carbon is secondary carbocation. Then whenever the husband is left behind because the wife, the living group has left him, then now you have to see how many social support that carbon is going to have. By social, I mean to friends. Now he has 2 friends. That's what we call that secondary carbocation. We're going to see that the next example we have. Tertiary carbocation, the crying husband, by the carbocation, I mean, he has 3 carbons adjacent to that. You have also primary carbocation, which is only 1 carbon. Now, the secondary carbocation, it's there, it's relatively stable. And there is also one thing. The other thing, in the next example, which I'm going to solve, I'm just going to show you the relevance of the carbocations in terms of the direction that it imposes in terms of the kinetics of the reaction. Next example, we're going to see why did I care about the social supports of the carbocation. Next example after the break, you see what do I mean by it. We talk about the kinetics in that sense. Now, this carbocation, which his wife left him, is crying because he's alone, positively charged. In terms of the terminology, it is very energetic now. Very energetic because it's charged. And if it has a charge, you have to, you see that in the energy of the energy becomes so high. You cannot have that one. But now, guys, look at that. If you want to come to the front, there is no need to argue for that. The front seat is always welcoming you. Adita, come back. Please come back there. Yeah, come back there. Adita, no, please come over there. No worries. No. Look at that, there is no argue. Anyone who want to come to the front desk, I'm totally fine with it. Please, sit over there. Now, you want to come to the front also? Then you go back. Now, let's finish this one. We just go take a break. The next example is then more fun. Now, this is a very critical step that you just want to do right now. The husband, which is left behind crying, he needs to marry again. Imagine you are married, You lose your wife, you have to get married again. And where do you go to find another girl for this? Look at this one. Look at the water which I had here. Hydrogen, hydrogen. This water molecule, which it has, this is in vicinity, and it has two lone pairs of the electron, which that two lone pairs is not part of the resonance hybrid structure. It's available. The availability of that free electrons on the oxygen, it's a signal says to that husband, I'm free to get married. Then what happens is this one. This one comes, we show that, we call that nucleophilic attack. It means that the water molecule which we had over there, it acts as what? Lewis base. Remember from last week? We said that Lewis base are those compounds that they have lone pairs of the electron unconstrained, and they can donate that lone pairs to form a new bond. We call them Lewis bases. Those are structures that accept those lone pairs, we call them Lewis acids. Now look at this one, the water molecule gives off that lone pair, then it becomes what? Lewis base or nucleophile. Okay, now there's some terminology besides from this wedding stuff that we talk about. Now, then what happens? If they get married, it means that the lone pair that the wife is going to take inside, it becomes part of a bond. I'm just going to show this structure right now. Look at this. I had CH3 over there. I had this carbon which got married. I have CH2 and I have CH3. And this one, I'm just going to show the water molecule. And I show the water molecule here. But remember, let me show this one with a different color. Remember, these lone pairs, which I had part of the water, which it signaled to the crying husband and available to get married, it becomes part of what? Part of the bound. That's why I show that with different color. Now, what I'm left with then, only one lone pair is here, you see? Because one of them was spent to form the bound. Now, everyone's good so far? Now, what did I do now? What did I do now is this, that I formed a bond. When I form a bond, what do I need to do? I have to stop and find the formal charge of the elements that they are impacted by that bound formation. By the way, I forgot to also show this one. Remember, this one also, we had an hydrogen, this one, which I forgot to put it there before. Now, the thing which I'm going to do is that I'm just going to stand on top of the carbon, which was impacted by the bound which I formed, and put my hands in my pocket, throw the fishing net around it. You see? The fishing net is around the carbon. I ask myself, how many questions now? 2 questions. First, what is the atmosphere I'm standing on? I mean, carbon stands on which element, in which group of the periodic table? 4. Awesome. I have 4. The second question which I ask is that how many fish I have counted inside that net? I mean electron. I see I have 1 electron here, 1 electron here, 1 electron here, 1 electron. How many in total? 4. 4 minus 4 becomes how much? 0. It means this is great. The carbocation which I had before, which it was charged before, now becomes neutral. Good sign. The husband now, he's not crying. He find a new wife. Now, we just go to see what is the story of the wife. I go to the oxygen, which she also got impacted by the bound which you formed. I'm just going to stand on top of the oxygen on its head. I throw my fishing net around it. Now, I ask myself again 2 questions. I'm standing on top of the oxygen. What is my address there? Oxygen is group 6. Fantastic. How many electrons I have in my net? Let's see. I have one here, one here. I have three parts of the bounds, and I have two over there. 3 plus 2 gives me how much? 5. 6 minus 5? 1. Then you see, I got. You're going to see that. Now, let me erase this part. Let me erase myself from there. Now, then you see that something happened. The oxygen there, it becomes positively charged. When the oxygen becomes positively charged, here is a huge problem. A huge problem. For example, everyone knows Elon Musk. Yes, he's so rich with money. If you come tomorrow to here, you see Elon Musk is standing outside asking for $1 to just go to buy a coffee for himself. Aren't they going to be surprised? You do not expect him to beg for money because he has lots of money. Oxygen has lots of electron. Positive charge means electron deficiency, like Elon Musk with money deficiency. Then whenever we just come across anything in our course that we see oxygen is positively charged, it becomes an alarming sound for us that we do not expect to see oxygen positive charge. Then now we have to do something. In order to do something, I'm just gonna stop right now. We take a break. When we come back from the break, we are just gonna see what to do with this newly married couple to do with the positive charge they have. Any questions so far? No? Let me stop the share. Okay, now let me see. I have very good hot spot over there. Brother? You're fine. Okay. Now, I'm just gonna continue with this for what we did, and let's say to see that how can we just proceed with this part of the lecture. Now, this one, as I said, you see that for this structure, you got into a very, very huge trouble that you had this one, a part of, let's say, the interactions that we had. Paru, now this is your turn. Come over there. Enjoy the front desk. And the funny thing is that I see no resistance. When I say come, everyone says, okay. I see no resistance. This is good. Now, the problem that we have over there, let's see how can we just resolve it. No. No. Let's see how can we resolve this issue. The problem happened, if you remember, we just went for the break, was that the wife that we got over there for the breathing carbocation, which we had over there, the oxygen has a little problem. It becomes positively charged. And as I said, we do not see that thing happen. You're going to see that over that that the oxygen molecule gets a positive charge, and that's a problem. As I said, it becomes after Elon Musk becomes deficient of the money. Oxygen, because it has the highest level of the electronegativity, should not become deficient of the electron. If it happens, we have to resolve the issue. We have two methods to resolve this issue. The first thing is that I can say, okay, when I reach to this point, I say when I reach to this point, I'm going to say, okay, I have two options to do. The first option is that they call that heterolytic bound cleavage. Means that I can break the bound between the oxygen and carbon over there, okay? And because oxygen is more electronegative, the lone pairs which comes free from this is going to be given back to the oxygen. This is one way. Then it gets the lone pairs back. Then it gets again two lone pairs. Then the positive charge on the oxygen is going to be resolved. But you see that, you ask yourself, am I crazy to do so? Because if you do that, you are coming back from where you started. Because if you remove this bound, give the electrons back to the oxygen, you go back to the presence of the carbocation, then you see that the bromide can come back again to this one. And you come back to the beginning where you started. And that's not the way to just run a chemical reaction, because you want to proceed to reach to a compound. Then the thing that we can say is that I say it's not a very good solution to do so. I'm not going to do that, but I think I can do something. The thing which I can do is this. The strategy which I can come to devise is going to be this. I'm going to say that if I cannot break the bond between oxygen and carbon, I have another possibility which I can go ahead with that. Look at this one, the presence of the hydrogen, which is covalently bounded to the oxygen. I say, what happens if I can kidnap one of these hydrogens? By kidnapping, I mean I remove the bond between the hydrogen and the oxygen. For example, the hydrogen which I have over there. The good thing of this is that if I can find an element, a compound, which acts again as a Lewis space itself, it acts as a Lewis space itself, means that it has a lone pair of the electron, because why I'm looking into this, because look at that. Again, I have for the hydrogen, I have it positively charged, and oxygen becomes partially negatively charged though, because there is a huge contrast of electronegativity. Then if I can find an element, a compound, which can act as a Lewis space, which it means that it can donate the electron, it can grab the hydrogen away from this one, then I can resolve the issue. Imagine I have 2 moles of the water inside that beaker, okay? I have, for example, I had 2 bromobutane over there, plus two moles of the water. It means that I have, again, water in excess. If the water is in excess, I have 1 molecule of water still in that solution. Or you could have used another co-solvent, which the same co-solvent acts as a Lewis space itself. We are just going to see that in future. If this happens, you see that again, we have the same scenario. We see that, okay, hydrogen, because this is so loose with respect to the bond which it has with the oxygen, it's gonna leave away, go away, and leaves everything behind. Look at this. In the fight over the electrons between the hydrogen and oxygen is more dominant, much stronger, grabs the electron. Hydrogen remains positively charged, no electrons attached to that. Then if hydrogen becomes positively charged, no attachment anywhere, look at this, another molecule of the water. It has a lone pair of the electron. It can readily donate it and share it with this hydrogen, which becomes like that, and it grabs this hydrogen. Then what happens at the end? What do we get? I'm just going to write it over there in top. I'm not going to change the screen because I want to have everything in one single shot. Then you see that if this happens, the first thing that we get, let me choose this color. This is our initially compound, which we had over there. We had CH3. It comes with this C, which it comes with this hydrogen over there. There is 1 hydrogen, I'll show it there. I have CH2, which is this one, and I have also CH3. And I also have this OH. Now, oxygen comes with 2 lone pairs now, and it comes with 1 hydrogen because one of the hydrogen was taken away. This one, which we have over here, you are going to see that in a couple of weeks, becomes a very important functional group, which is the alcohol. Then as a result, we call this one, you do not need to know that, 2-butanol. All reminds you of the alcohol. We do not care about that. Now, we see that this molecule turns to this. Now, we remove the bond, and if you now stand on top of the oxygen, because oxygen was impacted by dissociation of the bond, then you have to ask yourself, I have to find a formal charge, because anytime I just remove a bond, I form a bond, I have to stop and find the formal charge. If you stand on top of the oxygen, you know what is your address. You are coming from group 6. If you draw your fishing net around the oxygen, how many electrons you have inside? Yes, 6. Look at that. You draw your fishing net. You have 2 and 2, 4. And you have 2 crossing of the bounds. You have 6. Then you see that you have 6 electrons in your net. Your address was 6. 6 minus 6 becomes 0. It means that, yes, we were able to neutralize a positive charge of oxygen. Then we are fine and happy with that. But on the other hand, what else did we form? We are not forgetting these structures. Look at that. The water which grabbed one hydrogen. What happens into it becomes these structures. Now, look at that. You have hydrogen, hydrogen, hydrogen. The third one is the one that they kidnapped. And now you have only one lone pair, because one of those lone pairs of the oxygen is spent to marry the hydrogen, which you take it away from that structure. You spend it for the wedding ceremony. Now you have only 2 oxygen. Now, we are staying here to say that, okay, what is going to be the formal charge? Becomes oxygen. You stand on top of the oxygen here again. You see that you are coming from group 6. Now, you draw your fishing net around the oxygen. How many electrons you have? 5. 6 minus 5 gives you how much? 1, exactly. Then you see that with that case, you created another positive charge on oxygen. You created that. Then you say, oh my God, again, I have that problem. I have again that problem of positive charge on the oxygen. Now, how to resolve it? Because again, I got into the same problem. I'm just going to write it here a little bit on the top. You see, we got this structure, H3O. It becomes a very popular thing for you. You remember H3, we call that hydronium from chemistry 1, which we call that hydronium is a very strong acid because it has a very high Ka value or very small pKa value. That's what we learned from last week. The acidity is going to be measured in terms of its strength by the value of the pKa. If the pKa value is smaller, the acid becomes relatively stronger compared to the other ones. Then now hydronium is a very strong acid. It dissociates, if you remember, inside the water compounds. Then you get what? H2, which is, let's say, becomes a liquid, and hydrogen, which is, the hydrogen becomes the ion in an aqueous format inside the solution, which it means that when you conduct this reaction, you end up with an acidic environment. The output have some acidity. The pH of that solution drops because you have excess of the hydronium in there, and hydrogen can just release the hydrogen there. But normally you do not end up with that. Normally you have another structures in there, like for example, ammonia, which takes that hydrogen away and the solutions becomes neutral, because you have to have also one other compound to be recipient of that hydrogen ion from hydronium. That's where we introduce maybe a co-solvent or another agent there that takes that hydrogen released from there. But now, then it becomes what we discuss now. It is essentially the first example of what did we discuss. How can you proceed with chemical reactions? How to identify, for example, the site of the reactivity in order to manage the reaction that you have. Now, this reaction that we discussed today, it is called substitution nucleophilic reaction because you substituted another compound with the leaving group. By the next example that we have, either this session or next, you're going to see that. Do you remember we said that in this slide, we said that this carbon that we had formed here, it becomes, we called it, it was a kind of a husband, which the leaving group as a bromide, it was an unfaithful wife who left him behind and divorced. And we said that the carbon which is left behind, the carbocation, we called it, we saw that he was crying. We needed social supports with him. And I said that the social supports in that case reminds you of how many carbons is around it. The more carbons around it, the more soothing you bring to that brief carbocation. In our example, we had secondary carbocation because it was connected to two other carbons as a social networks around it. However, by the next example, you are going to see that a tertiary carbocation, secondary carbocation, and the primary carbocation exists when the leaving group departs. Then in that case, you are going to come to decide the kinetics of the reaction. Then we just merge into two classes of these reactions. We're going to say SN1, which the kinetics depends only on the concentration of the substrate. In the cases that we have, let's say, for example, for the case of that you have tertiary carbocations, we're going to come into that. Or we have SN2 reactions, that the reaction happens with the kinetics of two substrates and the nucleophile. The kinetics becomes dependent on those two ones. I'm going to not talk about that because it becomes confusing. I'm going to show that when we just come with an example. But at this stage, as a final point for today, remember the husband that we had over there, the crying husband, which is a carbocation, the number of the carbons around it, which we call it as the social groups, which forms tertiary, primary, and secondary, makes a huge impact on the kinetics of the reaction as we move forward. We're going to talk about that next session, okay? But we finished it right now with this example, which we included many things to move. What you saw over there becomes a fundamental way to orchestrate a reaction in organic chemistry. But it comes in more details. We talk about that next week. Okay, any questions? No?